In this video, I'd like to introduce our paper on the observation of a flat band and band gap in millimeter-scale twisted bilayer graphene, which was published on December 14, 2021. Twisted bilayer graphene is two graphene layers, stacked with rotation. In twisted bilayer graphene, the electronic structure can be modified by the interference of the rotated graphene bands, that many researchers have been focusing on in these 10 years. In particular, in 2018, superconductivity was reported in twisted bilayer graphene with a twist angle of 1.1 degrees, which is now called the magic angle. The origin of the superconductivity is related to the large density of states at the Fermi energy due to the flat band, which is shown by the red arrow in the figure. As for the direct observation of this flat band, two research groups published papers in early 2021. Groups in US and Switzerland reported these results in the same issue in Nature Physics. They fabricated twisted bilayer graphene with the twist angles of 1.34 degrees and 0.96 degrees, and observed their band structure by angle-resolved photoemission spectroscopy, ARPES. They said that the flat band could be observed at the Fermi energy, as shown by red arrows. However, in both experiments, the sample size was as small as about several tens of micrometers. In order to perform various other experiments and to realize the twistronics, large area sample is required. On the other hand, we have been made millimeter-scale single-orientation graphene by thermal decomposition of silicon carbide in these 10 years. If we can make twisted bilayer graphene by transferring this graphene, the sample size will be millimeter-scale, which is more than 5,000 times in area. As for the transfer of graphene on silicon carbide, Professor Kim at MIT, our collaborator, established the original transfer technique. Based on these background, in this study, we tried to fabricate large area magic angle twisted bilayer graphene by transferring graphene on silicon carbide, and to observe the band structure including the flat band. Sample preparation was done by the following procedure. First, monolayer graphene was grown on 5 by 5 square millimeter silicon carbide substrate. We deposited gold thin film on graphene, and exfoliated graphene together with gold using thermal release tape. We then transferred it onto another graphene on silicon carbide with certain twist angle, and finally, tape and gold were removed. In this study, the target twist angle was 3.0 degrees and 1.1 degrees, and the latter is actually the magic angle. We characterize these samples by these techniques. Now, I'd like to introduce our experimental results. Here is the results of twisted bilayer graphene with a target angle of 3.0 degrees. The left images are atomic force microscope images of two graphene samples before transfer. In the phase image, bright areas correspond to the monolayer graphene region, and its coverage was about 85%. In these two samples, we exfoliated the upper graphene, and transferred it onto the lower graphene. The left bottom graph shows the Raman spectra, and the top right graph is the magnified one. Graphene on silicon carbide 1 exhibited very sharp 2D band, indicating the presence of monolayer graphene. On the other hand, the 2D band after transfer is broad and asymmetric. This result indicates that it is bilayer graphene. In addition, there is a peak at the right shoulder of the G band, which is known as the R' band. R' band is often observed in twisted bilayer graphene. The right bottom image is the optical microscope image, after transfer with a strongly highlighted contrast. Bright area around the edge is monolayer graphene on silicon carbide 2, and graphene was transferred in the wide darker area. In other words, this darker area corresponds to the twisted bilayer graphene. The twist angle was 2.1 to 3.2 degrees, which was estimated from the angles between the edges of graphene and the substrate in this image. We performed ARPES measurements of this sample to investigate the electronic structure. This is the ARPES image around the center of the sample. In the left image, we can see two bands with the strong and weak intensities. Both have the graphene-like nearly linear band dispersion. Taking the electron escape depth into account, the strong band shown by the red arrow is from the upper graphene layer, while the weak band is from the lower graphene. The Dirac points of each graphene located at the positions shown below. Different Dirac energies indicate that the doping amount is different in the upper and lower graphene. And, the fact that the distance of these two bands was about 0.09 angstrom inverse means that two graphene layers were rotated by about 2.9 degrees. Then, the calculated bands of the 2.9 degree twisted bilayer graphene without the interlayer interaction are overlaid as the blue and red lines in the right figure. By comparing the experimental and theoretical results, we can find that there is a gap at the intersection of the blue and red bands. This means that this twisted bilayer graphene has a strong interlayer interaction. We did the same experiments at different points of the same sample. The photo shown in the middle is the sample holder and the sample in it. The results in the previous slide were obtained at the blue point on the sample. At the red points, two bands with the band gap were observed. This is the evidence of 2.9-degree twisted bilayer graphene with the interlayer interaction. At the black points, only the lower graphene band was observed. The area where the red points existed was about 3 by 5 square millimeters. This means that the twisted bilayer graphene with at least 3 by 5 square millimeters size was obtained. The next is the results of twisted bilayer graphene with the magic angle, 1.1 degree. The left figures are AFM images before transfer. From the phase image, monolayer graphene coverage was about 91%. Graphene on silicon carbide 1 was exfoliated, and transferred onto graphene on silicon carbide 2. The right figure is the optical microscope image after transfer. Twist angle, estimated from the angle between the edges, was 0.6 to 1.0 degree. We then performed ARPES measurements of this sample. The top left figure is the ARPES image. As shown by blue and red arrows, multiple bands were observed. The intensity profile of Kx equals 0.016 angstrom inverse is shown on the immediate right. Interestingly, the intensities of -0.22, -0.37, and -0.51 electron volts were stronger as shown by broken lines. The calculated band structure of 1.1 degree twisted bilayer graphene without the interlayer interaction is shown at the left bottom figure. This is consistent with the experimental result. On the right, the spectral function of the 1.08 degree twisted bilayer graphene, calculated from the band structure with the interlayer interaction is shown. Flat band is observed as shown by an arrow. The intensity profile along the Kx equals 0.016 angstrom inverse line is also shown above. These experimental and calculated profiles agree well, with respect to the peak positions. The upper right shows the experimental result rotated by 90 degrees. The peak in the middle corresponds to the flat band. From the above results, we succeeded in direct observation of the flat band in the large area magic angle twisted bilayer graphene. This is the first time that not only the higher binding energy region of the flat band, but also the lower energy side were experimentally observed. In summary, we succeeded in fabricating millimeter-scale twisted bilayer graphene samples, by transferring graphene obtained by the silicon carbide thermal decomposition. We also succeeded in observing the flat band in the magic angle twisted bilayer graphene. That's all for this presentation. Thank you for listening.